Welcome to the Trenton Computer Festival. This topic is the promise of solar energy. Solar energy is actually a wide family of systems. Oh, I won't step down here. Oh, here we go. Okay, I got it. All right. All right, it's a wide family of systems. On the right side, we have solar thermal, which is I'm sorry, we just had to get things set up here. On the right side, we have solar thermal, which can be either direct or stored heat. And we're thinking here of systems that concentrate sunlight to produce high enough temperatures to run a Rankine or steam cycle, either reciprocating or turbine, which can then either do work directly, such as pumping water, or spin an electric generator. If the system can store enough heat, it can even continue to generate throughout the night. We also, of course, have non-concentrated, low temperature solar heating, flat plate, for water and indoor space heating. Now, moving to the left, we have photovoltaics, which is our main topic. And the dominant technology here is silicon crystal, either single or monocrystalline or polycrystalline. All this stuff will be defined later in more detail. And the second major category is thin film. And the only one here that's silicon is amorphous silicon. And we have CIGS, copper, indium, gallium diselenide, cadmium telluride, some organics that are being worked on, and perovskites, which are a very promising new technology. Let's get into some photovoltaic theory. Photovoltaic effect is a process by which semiconductors convert light directly into electric current. Light is both a wave and a particle, which we call a photon. This is a principle which Einstein was first to explain in his 1905 paper on the photoelectric effect. This is the work that won him the Nobel Prize. The Planck equation we have here shows the relationship between photon energy and the wavelength or frequency of the light wave. And here E equals h nu. Nu is the usual symbol for frequency, or h times c over lambda, where lambda is the wavelength. These are the conventional symbols. And the constants are, h is the Planck constant, which is 6.6 times 10 to the minus 34 joule seconds, and c is, of course, speed of light, which is 3 times 10 to the 8th meters per second. In these MKS or S System International units, this is rather awkward, but for wavelengths in microns or micrometers and electron volts, it's very simple. E equals 1.24 divided by lambda. We plot this on a graph, and you can see that as wavelength increases, we go from the ultraviolet all the way down to the infrared at 1 micron. And this black stripe indicates the portion of the electromagnetic spectrum that is visible light. Now let's examine how this works in a photovoltaic cell. Here's our definition of photovoltaics. In short, the energy of a photon raises an electron in a semiconductor from the valence band where it's bound up to the conduction band where it's free to move about. A p-n junction provides a field to accelerate electrons and holes, the p and n doped regions respectively, and thence to an external circuit. Now, silicon is an element with a valence of 4, like carbon. So it makes covalent bonds with 4 other silicon atoms to form its crystalline structure. Photovoltaic cell consists of 2 layers of crystalline silicon. The upper layer is usually doped with N-type, having excess negative charges, and this is accomplished by adding traces of a valence 5 element, such as phosphorus, at part per million levels to the otherwise pure silicon. When the silicon forms its crystal, each phosphorus atom fits into the lattice and replaces a silicon atom. But the extra electron, that fifth electron, is left out of the bonding structure, so it's free to move about. Now, your lower level is doped p-type, p standing for positive, with valence 3 elements, such as boron. It leaves an electron vacancy in the bond structure, which we call a hole. Now, since conduction elements are able to move about, one can jump into the vacancy and leave another vacancy. Thus, the hole can effectively move about. Think of an underwater bubble, which is actually a vacancy in the water, that can be thought of as though it were an actual object. The hole is thus an absence of a minus charge, but it can migrate and behave as though it were an actual positive particle. When the p and n layers are in contact, electrons from the n layer are drawn to the holes in the p layer. Once they cross the boundary, their absence from the n layer creates a charge imbalance, a shortage of electrons and a net positive charge. The same principle applies to holes migrating from the p layer to the n. This imbalance creates an enduring electric field across the boundary. The region between the layers, where the most of the free electrons and holes that migrated out, is called the depletion zone. Now, if a photon enters the depletion zone with sufficient energy to dislodge an electron from a silicon atom, which is called the boundary value or the threshold energy, the electric field draws that electron to the n layer and the hole to the p layer. And these photon-liberated charges are what deliver the photovoltaic current. And this is an important idea here. Band gap and spectral response. Only photons whose energy is greater than the band gap can generate electrons and hole pairs. And it doesn't matter how many of them there are. Either the energy is sufficient or it ain't. If the energy is less than the band gap, that lets you create no charge carriers. The photon can pass right on through the layer. If the energy is greater than the band gap, the excess energy above the band gap is wasted as heat. For instance, if it takes 2 electron volts to satisfy the band gap and your photon has 3, that extra electron volt is wasted as heat. Now, this is very important because we're dealing not with monochromatic light, single wavelength, but the solar spectrum. And here the solar spectrum extends from the ultraviolet all the way to the far infrared. And if you look here, the black line is the ideal radiation from what's called a black body radiator at 5520 Kelvin. The yellow is the actual radiation the sun emits to see if you were above the atmosphere. And by the way, that's what solar-powered satellites. Down here, the red is what we see when we get down to the ground because the atmosphere filters out some wavelengths. So if your photon has an energy over, say around here, can you guys see the arrow? Okay.
Yes.
If your photon energy is around here, the photons with greater energy will contribute, and those with less energy will not. But those which are above, those which are above are going to have wasted energy. So there's a theoretical limit to the efficiency. Now, if this sounds a bit complicated, they're extremely helpful animated films on YouTube, and they're listed in the handout, which will be posted on the TCF website when those things do get put up. But let's divert for a moment, look at the history of photovoltaics. The PV effect actually has a long history dating back to the 19th century, but it's only comparatively recently that it's become efficient and cheap enough to be a commercial power source. Public interest began with the cells which powered early satellites, but commercial PV began in the 1970s following the Arab oil embargo. President Jimmy Carter, with his engineering background, recognized that renewable energy would reduce our dependencies on fossil fuels, petroleum, and reduce air pollution. To demonstrate his dedication, he installed solar thermal panels, flat panels, on the White House roof. That may be El Presidente over here, I'm not sure. These were not photovoltaic, but the goal was mainly to show dedication to solar. Carter also created the Department of Energy and initiated substantial funding through grants and subsidies to kickstart an industry, which would commercialize solar. Numerous companies rallied to the call, including the Cronach Corporation, where I worked for a long time. It was located right here in Lawrenceville. SolarX, which had their thin film division right across the river in Pennsylvania, and I consulted those guys after Cronach there. And believe it or not, newly created divisions of the oil companies. Now, the latter were largely greenwashing because the oil companies were taking a lot of static during that time. But still, the staff at ARCO, BP, and Exxon Solar were dedicated, and they advanced the technology. The U.S. became the major global producer. But then came January 20th, 1981, to be more exact, at noon Eastern Time, when Ronald Reagan became president. He cut virtually all clean energy and environmental funding, canceled environmental protection rules and regulations, and even took the panels off the White House roof. American companies' business plans had assumed that the subsidies would decline gradually as the industry became self-sufficient, as had such programs in the past for railroads and aviation and all that. But the sudden shutoff, most collapsed. And about shortly thereafter, new solar companies picked up the technology in Europe, Japan, and later China, because in those countries they enjoyed public financing. They took over the market and evolved the technology toward ever cheaper, more efficient products. So let's see how that happened. Let's talk about performance. A single cell has an output of less than a volt and a current of milliamps. We can combine them in a series parallel circuit, form panels and arrays. Here's a single silicon cell, about 4 inches square. Here's a panel about 2 by 3 feet with a whole bunch of these interconnected. And here we have an array, which is made of a bunch of panels or modules, and it's about 10 by 10 feet. They can be much bigger if you wish. Now, the efficiency of a photovoltaic cell, excuse me, is the amount of electric power it delivers per unit of light power striking the cell. Just as with any efficiency, what you get out is what you get out divided by what you had to put in. Testing is usually done under an intensity code, which we call 1 sun, which is, by convention, 1,000 watts of light power per square meter, measured at the device's peak power point. Peak power point? Yes. Oh, I'm sorry. Beyond, here's the next level of solar. It's the solar field. Now, here's the peak power point curve. If you take a solar device, the panel, module, etc., and connect a voltmeter across it, you'll see the peak voltage that it can enjoy, that it can put out, the maximum voltage, because you're not loading it down, you're not dropping the voltage by loading it. But since power is the product of voltage times current, and the current obviously is 0 at this point, the power is also 0. On the other hand, if you clip an ammeter across the device, it will be presented with a short circuit, and you'll see the circuit's maximum current, ISC, short circuit current. But once again, since the voltage is now 0, the power is 0. But there's some happy spot in between, which we call the peak power point. Incidentally, another term that's important is the ratio of the area under the rectangle formed by the peak power point divided by the ratio of the area formed by the ISC and VOC. Is called the fill factor. In other words, how much does the actual power curve fill the theoretical maximum? Although we now have automated instruments to do it, a classical measurement uses a watt meter to measure current, the peak, to determine the peak power point. So a watt meter measures simultaneously the current, the product of voltage and current. Not a new invention. It's been around for over 100 years. By the way, the best in the world were made right here in Newark by the Weston Electrical Instrument Company, and I have is a Weston. And that this looks like the peak power. The peak power. So you take this variable resistor or rheostat and tune it until you get the highest reading on your watt meter, and that's your peak power point. Okay. Knowing any two, current, voltage, power, or resistance, Ohm's law lets you calculate the rest. By the way, the peak power point can vary with changes in the illumination, both the wavelength distribution and the intensity. Once again, efficiency is the electric power out divided by light power in. Well, there are limits on efficiency. We hinted at them earlier, and these include things like surface reflection, light getting absorbed before it can reach the junction, photons passing through the active layers, photon energy too low or too high, and we looked at that before, recombination, where electrons and holes recombine before they can reach the N and P layers, mismatches between cells and modules, resistance losses, and if you're converting to AC or regulating your DC, converter losses. But big inverters today are 98% efficient, so better. So I wouldn't sweat that one too much. Of particular importance is the mismatch of photon energy with the band gap of the cell. Broad wavelength distribution of the solar spectrum means that any single junction device will have a maximum theoretical efficiency based on the spread of that spectrum, known as the Shockley-Queisser effect. This is the same Shockley who was involved in the invention of the transistor and several other key devices. Queisser was a fellow who was at the time. Shockley-Queisser efficiency limit, since only a single wavelength within the spectrum will exactly match the band gap energy and be exploited fully. One can draw a curve showing how SQ limits vary under sunlight as a function of cell band gap. And on this one, we can see where some of the popular cells lie on the curve. Selenium is way off to the in the long wavelength. Infrared. I mean, I'm sorry. Selenium is way off to the ultraviolet mostly. This is electron volts, and here we have germanium, which is way down in the low energy. But our good friends silicon, indium phosphate, and cadmium telluride are right up there near the max, which comes out to about 32 or 33% efficiency. That's the maximum efficiency you can get under this spectrum of sunlight for a single junction. But there are ways to get better. One way to beat the SQ limit by stacking two or more junctions with a higher efficiency, the higher energy ones on top. Photons below the, but also there's peak power tracking, sun tracking, anti-reflection coatings, reflectors, and concentrators. Let's look first, though, at that last item, the tandem cell. Here we have an incoming full spectrum. The blue end of the spectrum gets captured by the high band gap cell. The longer wavelengths, lower energy, sneak right on through. But down there, a low band gap cell gobbles them up, and you get better efficiency than you can get with any single junction. Now, since real photovoltaic installations do not, let's look at some of the other limitations. Since real photovoltaic installations do not enjoy constant direct sunlight all day, They can exploit two forms of tracking. The first is a power conditioner or inverter that constantly adjusts below the array at its peak power point. The second is sun track. Since the power collected by the panel is going to fall off approximately as a cosine of the angle that you're off perpendicular, and here we have a set of arrays. This is the International Brotherhood of Electrical Workers, Electricians Union, which is pretty interested in solar. That's in front of their headquarters building in Patton. Notice I'm pronouncing it correctly. Mechanical tracker keeps the array aimed at the sun as it crosses the sky. Now let's jump behind one of these panels, and here I've taken a photo of the motor equipment that keeps those cells aimed at the sun as it moves across the sky. And sun tracking can boost the harvested energy by about 25%. It also flattens the power curve so it doesn't peak quite so sharply at noon. Recently, however, as photovoltaic arrays have become cheaper, it's usually more economical just to put up more panels, aiming them in a southerly direction, if you're in the northern hemisphere, and at latitude tilt, that is 40 degrees above horizontal. 40 degrees above horizontal, because that's our latitude here. But there may be variations based on diurnal and seasonal demand. For example, if your main function of your panel is to run an air conditioner, well, the air conditioner has its maximum demand afternoon, so you may want to aim a little bit west of south. And since the air conditioner really has to operate in the summer when the sky is higher than the winter, you might want to be more flat to the ground, closer to flat to the ground. Now, there's a whole bunch of alternative photovoltaic cells. Now, unless the area of the cell is severely limited, for example, aboard a spacecraft, efficiency is not the sole consideration. Would you want to install modules that are just a few percent more efficient, cost 10 times as much? Of course, there are limits. At the other end, just as price, kill economy at the high end, balance of system costs, can kill you at the lower end. After all, there's a cost to the extra real estate, supporting structures, wiring, and maintenance. This reasoning has led to the invention and marketing of alternative photovoltaic technologies. Here are our main classes of cells. There's monocrystalline. You can see it's all one crystal of silicon. Look at the poly. You can see it's really a bunch of crystals that are sort of joined together to form roll crystals. And then there's what we call thin film, which is deposited on a surface. The most common alternative to single crystal is polycrystalline. And as I say, although it's a little less efficient, it's easier to make and cheaper to produce than a single crystal. Also, an interesting point is that the bars of silicon, which one saws the wafers with a diamond saw, are square rather than round. So you don't waste as much material forming your module or panel, because neither do you have to chop off material to make a perfect circle, make a perfect square, or you would with mono, or waste space in the module because you're trying to bunch a bunch of circles together with gaps between them. This monocrystalline is a compromise. You notice it's not a perfect square, but it's not a circle either. Another item which has reduced the cost of both mono and polycrystalline is that the diamond used for the diamond saw is now predominantly synthetic, which is a lot cheaper and of higher quality than dug-ups. The main group of alternatives is thin film, as I said. And with the exception of amorphous silicon, these all use semiconductors other than silicon as the active material. Some of the most recent are undergoing rapid improvement. And here we have a graph showing the improvement of lab cell efficiency. By the way, all this is going to be posted on the website, so you need to study these graphs in more detail to be able to do so. But you can see that the ones that have been around a long time, like monocrystalline silicon, have shown a gradual improvement from 1993 to the decades to the present time. But some of the more recent stuff, like especially perovskite, some of the organics, which is still not very good, but they're rising, and multi-junction has climbed quite rapidly, although it looks like it's going to be leveling off pretty much. Here is the current state of the art. And these, once again, are lab cells, by the way, and lab modules, which are generally small and chosen to be the best for test purposes. Commercial ones are going to be a wee bit poorer in quality, but you can see that the monocrystalline is at the top as a single cell, a little bit 26.7%, about 24.5% for a module. Multicrystalline is about equal to, multicrystalline single is about equal to mono modules. Single crystalline, silicon multicrystalline module is getting poorer, and so on. And here's our perovskite and perovskite modules, which are still undergoing evolution. Some thin film panels, by the way, can serve not just as rooftop panels, but be themselves the weather roof. These are some amorphous silicon panels, admittedly are not terribly efficient. They were made by the Kronar Corporation years ago when I worked there, and they are actually serving as roof shingles. They are, as I say, amorphous silicon. So they save money because you don't have to put on both shingles and solar panels. And if they're semi-transparent, it can even allow some of the sunlight to penetrate and illuminate the inside of the building. And this is a lab that Smithsonian has at Focus, Panama. Once again, Kronar amorphous silicon cells on the roof. Notice a relatively flat tilt because they're closer to the equator. By the way, a recent development is that's still not commercialized yet, is a panel transparent enough that it can serve as a window, sort of looking like tinted glass, where you can see through it. And that would be installed in what we call BIPV, or building integrated photovoltaic. As research and development continues, efficiencies have risen over the past couple of decades, especially for the newer types. Perovskites are a promising alternative. Perovskite describe merely a crystalline structure rather than a specific chemical composition. And they can be made with a variety of band gaps, enabling them to serve in tandem or multi-layer cells, either combined with silicon or other perovskites. And here's a chart showing a summary of cell types. It's a pretty complicated one, but they show the types, the efficiency percent, cost dollars per watt, advantages, disadvantages, and comments. Once again, I'm not going to go through all of it now, but if you want to study it, it should be up there when we get a chance to post. A big problem that researchers are attacking with perovskites is a lot of the materials are chemically unstable and tend to deteriorate in surface. The presence of moisture, or even they deteriorate with the ultraviolet portions of the light spectrum. We've talked about economics on a off and on basis, but let's get a little more into it. First of all, efficiency versus price. As stated earlier, at the low efficiency end, balance of system may kill the economy. At the high end, one must balance the cost per super efficient module versus that of putting up more of a cheaper, somewhat less efficient module. This trade-off is constantly changing as technology evolves. And here we have a price per watt of this is sort of a collective value for the modules in general. And you can see that just in 2007, they were more than $7 a watt. And now they've dropped down to about $1 a watt. Falling costs also appear linked to production levels. Obviously, mass production reduces cost. This is what economists call the price learning curve. And note that the axes on this are logarithmic, covering a huge range here. The cost the cost per watt seems to fall by about 25 to 30% for each doubling of production. And the same guys who drew this curve have dared to project the future. And you can see that depending on the application and such, we're talking about dropping from about 8 cents for the least, most costly, to about 2 or 3 cents for the best, down to perhaps a penny or so a watt. There are two common indices for cost-benefit analysis: energy payback time and economic or money payback time. The first asks, how long does it take to generate as much energy as it took to produce the panel? Obviously, it takes energy to manufacture it. And this has to include all the steps from mining the minerals to delivering the finished panel. The second asks, how long does the panel take for its output to pay back the financial costs to produce it? Again, including all the inputs. It turns out that for modern panels, both payback times have declined to about 1 to 2 years, yet they last more than 25. Since sunlight affects output and hence payback times, these payback times and economics will vary with the location. So let's look here at our solar map. It shows the daily average over the year, average solar flux throughout the United States. And if you look around here in New Jersey, where we are, it's about 4.5. So we, on the average over the year, we see about 4.5, the equivalent of 4.5 hours of full sun each day. And some places are a lot better. It's important to note, or poorer, it's important to note that economic comparisons between conventional power and solar are influenced by a whole bunch of things, such as government policies, regulations, and economic principles. And these include, first, subsidies for various energy sources, which may favor either solar or competing systems. They include outright subsidies, oil depletion allowances, which are still in force, and extraction rights for minerals, oil, coal, etc., on public lands. And then we have carbon taxes or fees on CO2 emitting processes. There's an organization which is very active in this called Citizens Climate Lobby, CCL. They are pushing for a program where there would be a fee based on the carbon footprint, as we call it, for any fuel or product. And the money would, if possible, be refunded to the public. And that way we would avoid offending the anti-tax politicians. Then there's what economists call externalities. That is costs that lie outside standard accounting, such as environmental damage, climate change, and health impacts of toxic stuff that gets emitted. And finally, there's the timing of costs. For solar, the cost is almost all up front. We have to consider also the investment value of that money. By contrast, combustion power has the ongoing cost of fuel. And finally, there's recovering and recycling at the end of a panel's life, especially if it contains hazardous materials. For example, the cadmium in cadmium telluride is toxic and carcinogenic. So if a cadmium telluride panel ends up busted in the dump and groundwater, particularly if it's acidic or strongly basic, oozes through it, it will leach out the cadmium, and the cadmium will get into the groundwater, migrate to rivers and streams, and get into all kinds of places. It's going to be ugly. Well, now that we've examined photovoltaic panels and arrays, let's see how they can be integrated into practical systems. Here's a freestanding photovoltaic system. Even before solar was economically competitive, and before even the intelligent and ethical members of our community became concerned about climate change, photovoltaic saw use on individual buildings that were remote from the grid or whose owners sought some kind of independence. And we have a drawing of a freestanding system. And this consists of your array, usually a switch disconnected, and you have a maximum power tracking circuit, which we talked about before, a charge controller to put excess electricity into a storage battery, and the DC loads run directly off the charge controller. And then you have your inverter to make AC, which drives the AC loads. Note that this generally requires energy storage, typically batteries, because one of the things you want to do with electricity is to be able to turn on lights at night. Since photovoltaic generates DC, the system will need an inverter to power AC equipment, but device can run directly on DC and do so. Here's a summary of the characteristics of the off-grid or freestanding system. Suited to isolated locations, etc. Batteries require charge control. No, okay. Now we get into the grid connected system. Today, most installations are grid connected. The system powers the building when the sun shines, and any excess electricity that it generates gets sold back to the utility through net power metering. Here we have our PV array. Once again, a switch is connected. That's important because in the daytime, you can't turn the darn thing off. You have to work on it. These voltages can be a little more than you'd like to feel. Your maximum power tracking, the DC to AC inverter, and now you have a thing called the anti-islanding circuit, which we'll get into, for your local loads within the house, and the net power meter. And by the way, most electric meters with the rotating disc in there, they'll go both ways. And here's your connection to the mains utility. Now, clearly the system must include an inverter that synchronizes with the AC utility, but there's another feature called the anti-islanding circuit to disconnect the inverter from the grid when the grid is down or disconnected. This is a safety requirement. So, for example, if a fellow is speeding in his gas hog SUV and smashes into a utility pole, pulling down the wires not too far from the house, the mains are broken, and the inverter then will the anti-islanding circuit will disconnect the inverter, so it will not stuff hazardous voltages back into the mains to endanger the poor guy who has to fix the damage. Here's a list of the characteristics of grid-connected systems. They can exchange power with the grid, give or take, require an inverter, and also the inverter has to have a good sinusoidal waveform because it's feeding into the grid where they're fussy about that. It's also subject to standards and codes more than a freestanding system because it is connected to the grid. Storage is rare, but it is possible. Next level up is community solar. Rooftop systems have their disadvantages, such as being on a roof, where they're difficult to mount and service. I've been up there. I can verify that. Tough to work on a panel. It's in the middle of an array when you'd have to step on all the others around it to get at it. Some roofs lack optimum orientation and tilt. Now, a recent trend is toward community solar, where a neighborhood or village sets up a shared system in a nearby field. And by the way, New Jersey is leading the country in this. I just read in the Sierra Club magazine that there are something like 50 or 60 community solar systems are already operating in this state. Also, shopping malls or public facilities may erect PV arrays over parking lots on structures tall enough to allow parking in the shade beneath them. And that makes it comfortable for the cars themselves. You leave a kid in the car, he won't get cooked before you get back. Finally, we get to the big stuff. Utility scale is the largest solar installation. These utility scale systems are called farms or parks, and they cover many acres, generating hundreds of megawatts of power. The economy of scale makes these the most efficient, both electrically and economically. Here we have a huge solar park in India. They're best located on land fully suited to agriculture and other uses. For instance, a retired landfill or a deserty area. For all its energy storage now, for all its green advantages, solar power is intermittent. We've hinted at that before, both in our diurnal cycle and as a function of weather. Continental US, a fixed latitude tilt panel gets between 3 and 7 sun hours, 3 and 7 sun hours a day. 4.5 in New Jersey. During the off hours, the grid needs other sources. Wind, which is the other main green energy, is also variable. So we need some baseline. Nuclear is an option, but energy storage would certainly contribute a lot. Let's look at the main contenders here. We have the maximum. We have a whole bunch of them listed here. And once again, this is a chart we might like to look at online, but they include pumped hydro, which is megawatt power levels. Discharge times can be order of hours. They last 30 to 60 years, and they are 70 to 85% efficient. Compressed air, molten salt thermal, which is used with these steam systems, because having both the solid and liquid salts present and being able to exploit the latent heat means that the temperature remains constant as you discharge the heat, and therefore the steam engine. And by the way, in thermodynamics, we don't discriminate too much. Tips and turbines can run at the same efficiency and settings all the time. And then we have batteries and hydrogen flywheel. So let's look at the main contenders. All of them have their plus and minus properties and vary in round-trip efficiency. Round-trip efficiency is what fraction of the energy you put in can you later get back out. Pumped hydro. Pumping water is mature and reliable. Motors can serve as a motor can also function as a generator, and a rotary pump can also serve as a turbine. Thus, we can store excess electricity by pumping water up to an elevated reservoir here, and then retrieve the energy by letting it flow back down. And here the lower water source can be a natural thing like a lake or a river. This usually requires a height difference of at least 150 feet to be efficient. So it's topologically restricted to a fair degree. You can't install such a system out in the middle of flatlands. The round-trip efficiencies are pretty good, 70 to 85%. Compressed air is receiving some consideration. It's sort of the gaseous counterpart to pumped water. Use your excess power to compress air into a voluminous vessel, which can sometimes be an underground cavern, and then retrieve the energy by expanding the air back out through an engine or turbine. There are problems, however, because when you compress a gas, much of that energy goes into heat. Just feel the bottom of a tire pump when you've been working it for a while. If the storage system dissipates that heat before you get the gas back out, that's waste. So the estimated round-trip efficiencies range from 40 to 70%, lower value being largely the result of heat loss. Batteries. Batteries are an obvious medium, and as mentioned earlier, are already dominant in small and off-grid installations, but they can become quite costly at utility scale. In evaluating a battery type, one must also consider its lifetime, both in years and in the number of charge-discharge cycles it can endure before it craps out or loses capacity. At the moment, lithium-ion batteries appear quite promising and have round-trip efficiencies that range between 85 and 95%. There's a new kind of battery that's being developed called the vanadium redox flow battery. It's making its way into the storage business. The electrochemical energy is not stored within the cell, but in external tanks of electrolytes that get pumped through the cells, which convert the chemical energy into electrical, or the reverse when charging. The size of the electrodes in the cells determines the peak power in kilowatts the system can absorb or deliver, while the energy capacity in kilowatt hours is determined by the amount of electrolyte. This allows the designer to adjust the two variables independently, and a typical round-trip efficiency on these guys is about 78%. Now, hydrogen. If hydrogen reacts with oxygen, it produces water. That, by the way, is the etymology of hydrogen, water producer, water creator. And the reaction releases a lot of energy. It's exothermic, either as heat of combustion, as a hydrogen flame, or as electricity if the oxidation takes place in a fuel cell. We have a little schematic of a fuel cell, and here we have a little symbol of a light bulb as you load. Here you have I'm sorry, this. Okay, and here you have the symbol of the light bulb load. We can reverse the reaction through electrolysis. And here's your electrolytic, I misspelled that, electrolytic cell, where you have your battery, the power source, which provides DC to it. The oxygen bubbles out here, the hydrogen bubbles out here, and you collect it. Feeding in energy to split water into hydrogen and oxygen this way is how you make your energy storage. There are now experiments with reversible cells where the same device can work both as the electrolyzer and the fuel cell. Hydrogen energy storage has a very dedicated fan club. Storing electric power, however, the electrolytic hydrogen has lousy round-trip efficiency. Electrolyzers can run about 70% efficient, and the best fuel cells about 60. Figure another 10%, figure 10% lost, compressing the gas, and you get back about 38%. If instead we recover the energy by burning the hydrogen in an engine, auto cycle gas engine, we get about 20% efficiency. Hydrogen can thus be justified only when more efficient systems are impractical. But that doesn't rule it out. Green hydrogen can still have utility besides filling balloons and enabling you to talk in a funny voice. It offers high energy density, lots of energy per unit mass or volume. This is valuable in aviation, where it can replace gasoline, or for jets, replace kerosene. Hydrogen has even more watt hours per kilogram than do the petroleum fuels, even if you have to include the weight of the pressure tank, compressed hydrogen, or a cryo vessel for liquid hydrogen. Hydrogen's energy density is, of course, dozens of times that of the best lithium-ion batteries. And interestingly, almost any heat engine that can run on hydrocarbons can also run on hydrogen. In fact, for the gasoline engine, it has an equivalent octane of better than 100. Flywheels offer a means of short-term energy storage, only seconds or minutes. They're shown in the chart there, and they're especially helpful in replacing the inertia associated with the flywheel effect of steam turbine generators when they spin, and they can thus stabilize the grid against sudden changes in supply, or if a heavy demand is suddenly switched in. There are also some gravitational energy storage schemes that hoist up solid weights, building them into towers, or dropping them back down. And there are also some which raise lower a big fat weight down a mine shaft, all that kind of thing. A lot of them sound awful fishy.
Hey, John, I hate to interrupt. You have about 5 minutes left.
Roger, thank you. Solar energy has evolved enormously in the past few decades, to the point where it can become a major source of green energy in a world where there is an urgent need to phase out CO2 emitting fossil fuels. Here's a list of the solar advantages and the challenges. I'm sorry, challenges and the advantages. And here are the, give me another minute here. And here are the challenges for the engineers and scientists amongst us. Make existing photovoltaics cheaper and more efficient, develop new types, get those perovskites working, and maybe even new things beyond that. Energy storage, cheap, efficient, and safe, improve the balance of the system. Smart grids to exploit and integrate the variety of energy sources, and secure and reliable control systems to integrate the grid. Those last two are good for our digital and computer jocks. So that's the story, for folks. And I hope that we can make this work. Do we have any questions? I think it's best to just shout them out.
We do actually have one in the chat, so I don't know if you want to open that up and read it, or I can read it to you if you like.
I'm sorry. Close the screen share. You mean? Oh, I'm sorry. Open chat. I'm sorry. Let me see if I can find chat. Okay, I hit chat. Oh yeah, here we go. Oh, okay. Although they are called amorphous, are any of the two alternatives you mentioned, conventional monocrystalline cells, similar to the Ovshinsky technology? And is there any commercial implementation now? I'm not sure what Ovshinsky's technology was. Would you tell me a little? Somebody tell me a little bit more about it.
Jonathan, it says from Neil Ormos that Stan Ovshinsky worked for years on a solar cell technology that could be printed on a metal sheet substrate.
Yes, most thin films can. That's exactly what they can be done. Yes, they can be printed on metal sheet. They can also be printed on the more heat-resistant and durable plastics, so they can be flexible, and that increases your ability to install them in all kinds of new places. Yes, that is true. Thank you.
All right, we have time for maybe one more question, maybe another after that.
Yeah. Compare solar versus wind. Well, I mean, they both work. They both have become quite economical. Wind obviously is geographically restricted to where you've got reliable wind. Once again, wind is intermittent. You need storage. I don't know how you would make a very accurate economic comparison, but I think they're pretty comparable at this point. So wind requires more maintenance because of moving parts and gears and things like that, but it certainly works, and I'm very much in favor of it. There are occasionally some people get very upset about birds who can't solve the Fokker problem. That is, fly between the blades without getting hit by one. And but if you can compare that with the number of birds choked to death on the soot from coal-fired power plants, I think they're doing a lot better with wind. But anyway, anything else?
Yeah, can you compare, or actually, I think you worked on amorphous silicon for a long time. Can you tell us the current status of amorphous silicon cells?
Yes, they proved not to fulfill some of their promises. when we were working on them in the 1980s, they were good for about 6.5, 7% efficiency, and they've since been improved to maybe close to 10. But they have not gotten any better than that. Our hope was that given the very high cost at that time of crystalline silicon, that you would just put up more amorphous and you'd come out economically superior. But as the people in the industry, particularly in Japan and China, made the cost of crystalline and polycrystalline silicon orders of magnitude cheaper, that argument ceased to have much weight. So amorphous silicon is pretty restricted in its uses now. It's usually used for very small installations where a little extra area doesn't cost you much. But that balance of system and extra area really made it non-competitive. Does that pretty much answer it?
Yes, thank you, yeah.
Cronau went out of business, not because of that, but mostly because of there were some management problems. But the shut off of government funding killed Cronau along with a whole lot of other companies.
All right, I'm going to cut you off there.
Okay. Well,
Thank you so much, John. It was really interesting to hear about all the solar technology. And just for everyone else here, feel free to switch around with TCF track you're watching. In about 10 minutes, John Gibbons, who has worked as an architectural engineer, practicing all over the world, is going to talk about immobilizing your town for environmental impact. So stick around if you want to watch that. If not, thanks for coming.